Thanks a lot for the opportunity to talk to you about climate change at the Fertilizer Association of Southern Africa's Symposium. As you will note, the title of my talk is Climate Change Trends, which might differ from the conventional presentations that deal with climate change projections. There are two reasons for this. Firstly, I assume that most of you are already well aware of the extent of climate change projections. And secondly, and probably more important, is that very little is said about historical climate trends in public climate change discussions. Trends, in fact, can provide valuable information on the climate change pathway that we are on, which in turn can provide additional information on what is possible and what might be expected in future. My talk therefore deals with finding a balance between historical climate change trends and future climate change projections. As far as the content is concerned, I will firstly introduce you to the best available information we have on global temperature trends, where I will give a bit more perspective on these trends. This will be followed by looking at historical climates with an emphasis on Southern Africa. I will then talk about the contribution of greenhouse gases and specifically CO2 or carbon dioxide in global warming. This will be followed by an overview of South Africa's climate, whereafter I will briefly elaborate on climate change projections. I will conclude the talk by bringing a message of hope for the future, where we will look at adaptation information as well as practical climate monitoring and impact assessments. In this slide, we are looking at global temperature variation since the first industrial revolution in 1880. The red line gives temperature variations for the northern hemisphere, while the temperature variations for the southern hemisphere is depicted by the blue line. Temperature anomalies are calculated using a baseline climate extending from 1951 to 1980. Note that the most recent increase in warming is most obvious in the northern hemisphere. The warmest year on record is 2016, with a warming anomaly of 1.27 degrees Celsius in the northern hemisphere and 0.71 degrees Celsius in the southern hemisphere. It appears as if the southern hemisphere warms at a slower rate than the northern hemisphere, which might be attributed to larger continental coverage, higher population densities, and therefore more air pollution in the northern hemisphere. To put the anomaly graph of global temperature increases shown in the previous slide into perspective, it might be appropriate to look at the actual temperature graph. This temperature graph shows a slight increase in global temperatures of approximately 1.1 degrees Celsius over the past 140 years, with a current global average temperature of approximately 15 degrees Celsius. It is interesting to note that it is this temperature increase that had spiked the original awareness of global warming, which is in fact taking place. Scientists were concerned and therefore started with research on climate change, which not only provided some explanation on the warming that's taking place, but also resulted in some adaptation strategies. In more recent years, however, the global warming debate entered an extreme phase with words like climate emergency, climate crisis, and even climate collapse on the newspaper headlines. But let's look at the current warming from a historical perspective. Is it really this severe? One of the most comprehensive studies on global climate change takes us 1,600 million or 1.6 billion years back in history. It resulted in the graph shown in this slide. The red line gives temperature variations, while the blue line gives CO2 or carbon dioxide concentration variations. The average temperature over this period was approximately 5 degrees Celsius warmer than today, with the highest temperature ever at 9 degrees Celsius warmer than today. It is therefore obvious that the Earth is cooling down. Over the past 600 million years, both global temperatures and carbon dioxide concentration levels were significantly higher than today. Also note that there had been no clear relationship between temperatures and carbon dioxide concentrations, a phenomenon that had only recently been observed. Over most of the 600 million year period, life was present on Earth, with, for example, the dinosaur in the Mesozoic era that had existed in 8 degrees Celsius warmer conditions and much higher concentrations of carbon dioxide than experienced today. It was also over the Mesozoic era where vegetation thrived and where vegetation were deposited to provide the fossil fuels that we mine today. Even mammals developed in conditions that were 7 to 8 degrees Celsius warmer than today. It is therefore clear that we are currently living in a cold period in Earth's history. The question is, but why do we have these variations in Earth's climate? One of the best answers were provided by a Serbian scientist with the name Milankovic. We all know that the Earth receives most of its energy from the Sun, although this energy might differ from time to time because of various factors. Milankovic identified 3 factors which are related to the position and orbit of the Earth relative to the Sun. The first factor is linked to the tilt of the Earth. The tilt varies from 22.5 degrees to 24.5 degrees, which occur in a 41,000 year cycle. The hemisphere pointing towards the Sun as a result of the tilt receives the most solar energy, as illustrated by our current summer and winter seasons. The second factor is known as precession, which describes a 360-degree conical motion of the Earth's axis which occurs in cycles of 26,000 years. The third factor is called eccentricity, which determines the shape of the Earth's orbit around the Sun. The shape varies from a circle to an ellipse in cycles of about 100,000 years. It is important to note that the temperature or climate conditions in the northern hemisphere is predominant in driving the Earth's climate. Other factors like volcanic eruptions, etc., might also have an influence on Earth's climate, although the Milankovic cycles appear to play a dominant role. The combined effect of Milankovic cycles on Earth's paleoclimate is best observed in the analysis of ice and sediment cores. An ice core that provides one of the longest records is known as the Vostok ice core. The core was extracted from a 3.6 kilometer deep hole drilled by Russian, American, and French scientists between 1989 and 1994. An analysis of air bubbles trapped in the layers of ice can provide valuable information on historical temperature and carbon dioxide concentration variations. In the graph presented here, the orange line shows temperature variations, while the grey line shows carbon dioxide variations. The same variation patterns were also identified by other ice core studies, even in the northern hemisphere. 100,000-year eccentricity-driven cycles of longer cold glacial periods and shorter warm interglacial periods of approximately 10,000 years in length stand out in the Vostok graph. 4 such cycles were observed in the past 400,000 years, with the Earth currently experiencing a warm interglacial epoch known as the Holocene. This is against the background that we are already in a cold phase of Earth's longer history. Note that maximum temperatures which occurred in all 4 interglacial periods experienced before were all higher than the maximum temperature in the current Holocene epoch, where global warming is being referred to by some people, interesting enough, as climate collapse. By looking at the past 150,000-year record presented by the Vostok ice core analysis as shown in the top graph of this slide, one can get a better perspective on temperature variations in both the previous warm interglacial period and the current warm interglacial period known as the Holocene epoch. Note the relatively higher global temperatures in the previous interglacial period, which are approximately 2.5 degrees Celsius warmer than the temperatures currently being experienced in the Holocene epoch. One can examine the current warm Holocene epoch even in more detail by looking at an interesting paleo-temperature graph that was constructed by scientists from the University of the Witwatersrand. The orange line in the bottom graph, which takes us 1,000 years back in time, originates from a cave stalagmite analysis which was done at the Makapansgat cave in the Limpopo province of South Africa. The zero line represents the current temperature. It is interesting to note that temperatures experienced in southern Africa during the medieval period in the years 1000 and 1300, which is only about 800 years ago, were as much as 3 degrees Celsius warmer than today. After this medieval warming, South Africa entered a cooler period which is globally known as the Little Ice Age, from where we are currently recovering. These and other results illustrate that the Earth in South Africa experienced much higher temperatures even not so long ago. The question again is, can it be justified to use words like a climate emergency, a climate crisis, or even a climate collapse by referring to our current climate conditions? When talking about these significantly warmer periods in Earth's history, I'm not at all saying that the current warming that is being experienced cannot be attributed to human or anthropogenic influences. I am, however, think that it is important to put things into perspective by looking at the bigger picture of Earth's history and not to jump to unrealistic and extreme, in many cases politically orientated conclusions. There are in fact differences in the current global warming trend that we experience if compared to previous trends. One of the differences is that large quantities of carbon dioxide are being released into the atmosphere by human activities, something that never happened before. With this, CO2 is leading temperature changes in contrast to CO2 changes that followed historical temperature changes in the previous records. Another reality is that the current warming is not driven by solar variations. Our concern about anthropogenic global warming can therefore certainly be justified. The map on the left of this slide shows long-term temperature trends in the top map and more recent temperature trends in the bottom map. It is especially in the northern hemisphere where the warming is most noticeable. A recent study by the South African Weather Service pointed out that South Africa is warming at a rate of approximately 0.17 degrees Celsius per decade, that is every 10 years, which point to a slow temperature increase rate. However, if one looks at the left bottom world map, this rate accelerated to approximately 0.3 degrees Celsius per decade over the more recent 3 decades. While talking about global warming, one also needs to put the contribution of carbon dioxide or other greenhouse gases as a driver of temperature changes into perspective. Global warming, whether natural or anthropogenic, is driven by greenhouse gases in the atmosphere and the influence that these greenhouse gases have on the Earth's radiation budget. Water vapor is regarded as the most common greenhouse gas in our atmosphere, followed by carbon dioxide. On the left-hand side of this slide, an Earth without any atmosphere is depicted. With the incoming solar energy, known as the solar constant, and the energy absorbed and reflected by the Earth's surface, followed by the heat emitted by the Earth's surface, the global temperatures would have been minus 18 degrees Celsius. Remember that this is without any atmosphere containing greenhouse gases. But if one adds the atmosphere, the global temperature increases to approximately plus 15 degrees Celsius. This is a 32 degrees Celsius difference. A large factor in this warmer atmosphere is carbon dioxide concentration, which increased from 270 parts per million at the beginning of the first industrial revolution to the current 410 parts per million, certainly as a result of human interference. The question is how such increases will affect Earth's global temperatures in future. What many people don't realize is that the influence of carbon dioxide on temperature is not linear. In other words, the temperature will not rise by a constant value of X when carbon dioxide rises by a constant value of Y. In reality, scientists agree that the greenhouse effect is logarithmic. It means that as more carbon dioxide is added to the atmosphere, the effect of carbon dioxide on global temperatures will start to decrease. For example, if one doubles the pre-industrial revolution concentration of 280 parts per million of carbon dioxide in the atmosphere, one will get 560 parts per million, which might lead to a temperature increase of approximately 2.3 degrees Celsius. Another 2.3 degrees Celsius increase will thereafter only happen after a doubling of 560 parts per million, which will give us a value of 1,120 parts per million, and not after adding another 280 parts per million, and so on and so on. According to this calculation, a global temperature increase of approximately plus 3.4 degrees Celsius is expected in the year 2100. But this is significantly lower than projected by most climate models, which in the latest assessment report of the Intergovernmental Panel on Climate Change projects temperature increases of up to 6 degrees Celsius. The additional heating required to get a 6 degrees Celsius rise in temperature, however, comes from other radiation budget properties, which I will discuss in more detail a little bit later. A valid question is therefore whether climate models are capable of realistically simulate these additional warming properties that cannot be explained by the increase of carbon dioxide concentrations in the atmosphere. With a wider scope on historical climates and the contribution of carbon dioxide on global warming, let's now look at the South African climate. The most important thing to mention is that the South African climate is variable, and the reason for this is because our climate is influenced by different weather systems. South Africa is located in the mid-latitude of the world at approximately 30 degrees south. This is a region characterized by large-scale subsidence, meaning that air masses sink from the upper atmosphere towards the surface of the Earth, which do not create favorable conditions for rainfall. Secondly, moisture for rain comes from two different regions, namely moisture from the tropics for summer rain and moisture from the West and Southern Ocean for winter rainfall. Summer rain is only possible because of surface heat radiation, convection, and the subsequent precipitation of moisture flowing from the tropics. Apart from these factors, South Africa rainfall is influenced by remote ocean forcing, like for example the El Nino phenomena. The interaction between these systems makes the climate model projections for South African rainfall extremely difficult to produce, and from my view, sometimes almost impossible. However, temperature projections produced by climate models appear to be more realistic than rainfall projections. Or are they? In the previous Intergovernmental Panel for Climate Change Assessment report, temperature increases of up to 5 degrees Celsius were projected for South Africa in the year 2080, although even warmer conditions of up to 6 degrees Celsius are projected in the more recent and new 6 assessment report for the business as usual pathway into the future, also referred to as the RCP 8.5 pathway. Interesting is that an increasing number of recent scientific studies have warned that most climate models in the 6 assessment report are overestimating future global temperatures. The source of this overestimation might come from the difficulty in simulating additional radiation properties and feedback other than carbon dioxide warming by climate models. Most rainfall projections point towards drier conditions over most of South Africa, although with high uncertainty. But let's look at the radiation feedbacks that could influence Earth's temperature in more detail. One of the most difficult processes to simulate by climate models in a complex atmosphere is surface radiation balances and cloud processes, not even to mention for long periods in advance, like for climate change projections. For example, the heating of the atmosphere by carbon dioxide, which can be regarded as a scientific fact, will result in the melting of snow and ice. This melting might alter surface properties by exposing water and soil, which will absorb more solar radiation and in turn will emit more heat to the lower atmosphere, which might accelerate global warming. With an increase in global warming, more evaporation might take place from the surface, which might result in more cloud formation and rainfall, and which in turn might cool the lower atmosphere as a result of less solar radiation and evaporative cooling. These processes are not only extremely difficult to simulate, but even more difficult to project. Such difficulty will certainly contribute to uncertainties in climate change projections. However, the least we can say is that global warming is a concern and that we as humans must take action to reduce our footprint regardless of the extent of the projected warming. The only way to productively respond to climate change is not to only act in response to model-simulated climate projections, as it is done in many reports, but rather to look at both the historical climate and climate outlooks. Since the historical climate was observed, it is obviously much more certain than model-simulated climate projections. By looking at historical trends, one can already perform climate risk assessments to ensure a higher degree of resilience. One can also use this as a basis, with the help of model projections, to plan for the future. As summarized in this slide, climate change adaptation and resilience can be achieved in practice on a day-to-day, month-to-month, or year-to-year basis by following a sustainable rotating climate-sensitive route based on good observations, regular updates, risk assessments, and response planning according to observed weather and climate events, while aligning these to weather forecasts, seasonal predictions, and climate change projections as they happen at the location of interest. In more detail, the first step should be to observe your climate by weather station measurements, regular data collection, and the archiving of data on reliable sources. Secondly, one can now use the weather or climate data collected to perform statistical analysis. Examples are the calculation of averages, frequency of occurrence, or the identification of extremes. Information about the average climate at your location gives you a good basis from where you can work from, since climate outlooks are often given as anomalies or deviations from the average. Extremes, on the other hand, can provide valuable information about the climate boundaries in which you can expect to operate, which will also help you to adapt to shifts in climate, especially those shifts that pose the highest risk to your operations. Thirdly, with a good source of data and good knowledge of the characteristics of your weather or climate data, you can now make use of different weather and climate outlook products to plan for the future. The South African Weather Service provides short-term forecasts and seasonal outlooks which you can use, and various other sources, including the Weather Service, can also provide climate change projection information. But always remember to align your weather and climate outlooks with historical trends to ensure a consistent pathway extending from the path into the future. And lastly, it might be appropriate to experience your climate inside the framework in which you are operating, meaning that you should find links between weather or climate variables and the variables which are key to your operations. It will help you to formulate a better understanding of the impact of climate on your operations. It will also help you with identifying climate-sensitive indicators in order to reduce your risk or to become more climate resilient. From here on, one can again move back to new observations, updated statistical analysis, and continue on a sustainable rotating climate-sensitive route. With global warming and climate change as a reality, and with the influence of humankind regarded as a risk to sustainable development, I would like to convey a message of hope for South Africa. The South African Department of Environmental Affairs is one of the most active entities in the world, and certainly the most active in Africa, in developing and providing guidelines, strategies, and policies for acting on climate change. These sources are currently even available on provincial and municipal levels and are applicable for various sectors of society, including the agricultural sector. Instead of giving a detailed layout on adaptation and mitigation interventions, I would like to invite you to get hold of the information that's already available in this regard. I would like to thank you for giving me the opportunity to share my experience in climate change with you as delegates at the Soil Fertility and Plant Nutrition Symposium. You are more than welcome to contact me via email or call me if you have any questions or suggestions.